All right, today we're going to dive into a really cool corner of thermodynamics. It's called the enthalpy of solution. And trust me, it's the secret science behind a lot of things you see every day. So let's jump right in.
I mean, you've probably wondered about this, right? You grab one of those instant cold packs, you crack it, and boom, it gets freezing cold. Or on the flip side, maybe you've mixed something up and actually felt the container get warm in your hands. So, what's going on there? What's the science behind that sudden switch?
Well, the answer to that mystery has a name: enthalpy of solution. And I know, it sounds a little intimidating, but all it really is the name for the heat change, the energy that's either soaked up or given off when you dissolve something. And that is the key that unlocks the whole thing.
Okay, so here's our game plan. We're going to look at the heat of dissolving, this idea of an energetic tug of war. We'll check out two different ways to measure enthalpy, see how they connect, and then we'll put some numbers to it. Sound good?
All right, so first up, the heat of dissolving. What exactly is happening when you pour, say, salt into water and it just disappears? At its core, it all comes down to a simple trade-off. It takes energy to pull things apart, right? But you get energy back when new things snap together. And that final temperature you feel, it just depends on which side of that equation wins out. So let's dig into that a little deeper. We can really think of this whole thing as an energetic tug of war, and it happens in three key steps.
Okay, step one, you've got to use some energy to break apart the solute particles, the salt crystals themselves. Step two, you also need energy to shove the water molecules aside to make some room. So steps 1 and 2 are your energy investment. But then, step 3 is the payoff. That's when the salt and water particles finally get together, form new connections, and that is when energy gets released. And this graph shows that tug of war perfectly. See, we start here at some baseline energy level. Then for those first two steps, breaking everything apart, we have to put energy in, so the energy level climbs. That's the endothermic part. But then when those new bonds form, we get a big energy release and the level plummets back down. That's the exothermic part. Where we end up compared to where we started, well, that tells us the whole story. So it all boils down to who wins. If the energy you had to put in is more than the energy you got out, well, the solution has to make up that difference by stealing heat from its surroundings. And that's why it feels cold. That's endothermic, just like your cold pack. But if the energy you got out is more than what you put in, then there's extra heat that gets released, and that's why the container feels warm. That's exothermic.
Okay, so we've got the basic idea down. Now let's get a little more specific. It turns out there are actually two different ways to measure this stuff: integral versus differential enthalpy.
Let's start with integral enthalpy. The easiest way to think about this one is it's the total effect. It's the big picture. It answers the question, what's the total amount of heat that changed when I dissolved 1 mole of my stuff in this much liquid? It's the final score of our tug of war.
And the math for it? Super simple. You just take the total heat, which we call Q, and you divide it by N, which is the number of moles you dissolved. That's it.
Okay, so then there's the other type, differential enthalpy. If integral was the big picture, think of this as the super zoomed in, moment-by-moment picture. It tells you what's happening right now, at a specific concentration, if you were to add just one more tiny little bit of solute. It's the instantaneous effect. All right, so we have the total and the instantaneous measurements. How in the world do those two relate to each other? Well, let's connect the dots. This graph is awesome. It shows the connection perfectly. So what we're looking at here is a plot of the total, or integral, enthalpy versus the concentration. And you get this curve, right? Now here's the cool part. The differential enthalpy at any one of these points is just the slope of the line right at that point. It's literally the rate of change at that exact instant. So yeah, that's the big takeaway right there. The differential enthalpy is simply the rate of change of the integral enthalpy. One is the whole journey, the other is your speed at one particular moment. It's just two ways of looking at the exact same process. But what does that actually mean in the beaker? Well, think about it. Down here at low concentrations, the slope is pretty steep. That's telling us that those first few solute particles are interacting really strongly with the solvent. But as you add more and more and the solution gets crowded, that slope flattens out. The interactions aren't as powerful anymore. And if you could imagine a solution that's infinitely diluted, at that point, the integral and differential values would actually be the same. Okay, enough theory. Let's put some real numbers to this and do a little math. All right, problem number 1. Let's say we dissolve 2 moles of potassium nitrate, and as we do, the solution gets cold. It absorbs 10 kilojoules of heat. The question is, what's the integral enthalpy?
So we just need to pull out our formula for integral enthalpy. Remember, it's just Q divided by N. So we take our 10 kilojoules, divide by our 2 moles, and we get plus 5 kilojoules per mole. And that little plus sign is super important. It tells us that heat was absorbed, which means it's an endothermic process. And yep, that solution would definitely feel cold.
Okay, on to problem 2. This time, imagine we already have a solution made up. We're just going to add a tiny little bit more solute, say 0.02 moles. And when we do that, 0.6 kilojoules of heat is released. So what's the differential enthalpy at that very moment?
Once again, we just follow the formula. The differential enthalpy is that little change in heat, delta Q, divided by the little change in moles, delta N. And here's the crucial part. Because heat was released, our heat value, Q, is going to be negative this time.
Okay, so let's plug in the numbers. We've got negative 0.6 kilojoules divided by 0.02 moles, which gives us a differential enthalpy of negative 30 kilojoules per mole. And that negative sign tells us exactly what we thought. It's an exothermic process right at that moment. So you see, dissolving something is never just mixing. It's a dynamic energy exchange. It's this constant battle between the energy it costs to break bonds and the energy you get back from making new ones. Which leads me to a final thought. Now that you can see this as an energetic tug of war, what other things in your daily life can you see as this kind of battle?